Okay, in section 3.4, we are going to discuss how to use something called interacting particle systems to generate aggregation and segregation. Okay, we call this systems IPS. And IPS is a generalization of cellular automata. Okay, there are transition rules, but different from total CA. These transition rules, they are random or they are stochastic and can vary across space. Okay, and IPS systems, they are they are pretty good to produce something called collective behavior or emergence. Okay, collective behavior of stochastically interacting components, and IPS has pretty broad applications. They can be applied in different realms, disciplines. Okay, applications span the nature and social sciences. Later we'll say why it is so universal, okay? Because it's about the random moving of particles. So particle is a very broad concept. It has no context here, but you can give it context. For example, each human being can be a particle. Each animal can be a particle, okay? Or you can say physical particles like items or molecules. They are by nature particles, right? So let's say how to use IPS, how to use models to simulate IPS, and then simulate aggregation and segregation. So why interacting particle systems? Okay, it's a stochastic version of cell-based CA. Okay, there is continuous time. It is a continuous time version of stochastic CA. Okay, but when we're talking about continuous, it's always relative. Okay, it's always relative. It depends on the scale of your research. If your research time scale is 1 million year, then sampling every year is good enough to call it a continuous time sampling. Okay, it's the same thing here. It's always relative. Here, although in NetLogo, in agent-based models, we use a tick. We use a tick to address the change of time. It looks discrete, but yeah, we can consider it continuous if there are, say, enough ticks. And it can be used, IPS can be used to simulate a physical phenomena. For example, on the right side, we have this box or room. There is a board in the middle of the room, and in the upper half of the room, we have gray particles, right, mainly. But in the lower half of the room, we have blue particles. We have small arrows addressing the moving directions of each particles here. They're randomly moving in their space, upper half or lower half. But now if we remove this board in the middle of this room, what do you expect? These two types of particles, they are going to invade each other's space. If there is vacant space, they will, of course, they will randomly move. But there is always a trend that these particles, they will invade the vacancy. And also in GIS, IPS can be used to model collective behavior of stochastically interacting locations in ecology, biogeography, and maybe the spread of infectious disease population dynamics. urban dynamics. You may say that the movement of population is not that random. You are correct. But again, it's always a relative concept. When you are looking at a city, when you are looking at a population at city level, there is always a clear pattern about the movement of the population. But when you are looking at the individual level, we can consider the movements of individuals, for example, humans, or animals in the forest, in the wild. They are moving randomly, okay? And some specification of IPS, okay? Cells in a two-dimensional lattice, okay? This is the same as say A, okay? And the state transitions are stochastic. Okay, I will show you examples later, but now you should know that in summary, state transitions, they are random instead of deterministic. Function of the states in each cell's neighborhood, okay? This is similar to total say A, okay? The state of a cell at t+1 is a function of the states in each cell's neighborhood, in its neighborhood. And technically, transitions are a Markov process, which means it's memoryless, a stochastic process. I will explain a Markov process in general later, okay? Not in detail. And how to update. We're going to use synchronous updating for IPS, okay? Or we can use asynchronous. If you ask me which one you should use in your research, again, there is no correct answer for that. It depends on your specific application, and you have to decide that, okay? If you were using asynchronous updating, you need to randomly pick cells to update one at a time, okay? And let me show you some example and compare total say and IPS. So here we have total say with majority rules. If you remember, it means that the state of the central cell at t+1 is decided by the majority of itself and its neighborhood. We're talking about outer say, right? So itself should be considered. Okay, if this is the case at t, for total say, what's the state of central cell at t+1? So you just need to find out the majority, right? So 1, 1, 1, 0, 0. So majority is 1. So at t+1, you are sure, and it's deterministic that the state of the central cell will be 1. That's for sure. There is no randomness in this. Okay, and how about this situation? We have 1, 2, 3, 4, 5, 1, and only 1, 0. So the majority is 1. So at t+1, it will still be 1. Okay, okay. So this is a review of total say A. This is a review of total say A. Once the neighborhood states and its own state, they are decided. There is no randomness at t+1. Okay, it is the central cell state is decided. And what is Markov process? Markov process means that at a specific time, the state of a cell is only decided by its state at t-1. For example, t+1, t+2, t+3, +4, +5 until t+n. This is a timeline. And let's define that now we're at t+3. This is present. If this is considered, if you assume that this timeline is a Markov process, then the state of the cell at t+4 is only decided by t+3. it has nothing to do with t+2, t+1, or t, which means the history matters, but only the history before this tick matters. The state at t+4 is only decided by t+3, but not affected by any other historical time point. And of course, it is also has nothing to do with future. It has only, it is only decided by the history one tick before. Okay, so there is no memory. There is memory. There is only memory from the last tick. Okay, from t+4 is only decided by t+3, but not other history. Okay, so this is Markov process. It's a statistical concept and it's complex, but in this course, you just need to know this. Okay, let's get back to the slide. Okay, there are different types of IPS. Now let's start with the very basic one. It's called basic contact process. Okay, it's a type of IPS. So states, each cell is either 0 or 1, which means the state here is binary. 0, we call it vacant. 1, occupied. Or you can say a 0 represents the absence of a particle. 1 is used to address the presence of a particle. Transition rules. Okay, at the very beginning, we need to define a neighborhood, right? We use Van Neumann neighborhood. And asynchronous updating, which means we update cells one by one. So transition rules. Rule number 1, if the site is occupied, which means 1, particle dies, which means change from 1 to 0, with a set probability delta, which means you need to give a value to delta. It's a probability, which means delta is always somewhere between 0 and 1. Okay, and rule number 2, if the site is now vacant, 0, a new particle is born, which means change from 0 to 1, with a probability beta. Here comes the important part. Beta is decided by the proportion of neighboring sets that are currently occupied, which means that we use a probability here to decide if a particle is going to born or not. Here, it's not deterministic, it's random, it's stochastic, because we're using a concept called probability. Okay. So here is a model from your model library to show this basic contact process. I will leave it to you, but now more importantly, I'm going to show you the difference. I'm going to compare total CA and IPS. I just reviewed total CA with majority rules, right? There is no randomness. But given these two rules, especially rule number 2, what is going to happen in basic contact IPS? Okay, let me show you. It's the same neighborhood, same states, right? The central cell now is 0 and 1, 1, 1, 0. Okay, let me give you a specific probability for rule number 1. If the site is occupied, particle dies with a specific delta. Okay, now for this situation, because now the particle is not alive, so we don't have to set a specific delta for it, because it's a death rate, death probability. For this example here, the cell itself is alive right now, so we give it a probability. Let's just say 0.4. Okay, this is delta. And at time t, let's check this example first. As time t is 0, So how to give birth to this cell? How to give birth to it? A new particle is born with a probability beta given by the proportion of neighboring sets that are currently occupied. So now we have four neighbors, and 3 of them are occupied currently. So it means that 3 out of 4, which means 75%. That's beta, or 0.75. That's the value of beta. Beta is decided by the proportion of neighbors that are currently occupied. 3 out of 4. It means that the probability of giving birth to this cell is 75%, which means that it could be 1 at t plus 1. The probability of being 1 is 75%. It could be 0. The probability of a 0 is 25%. Now you know that. Now you see that there is something called probability and randomness here. In total CA, it will be 1 because it is simply decided by the majority of the neighborhood. It's 100% to be 1. But here, the state of the cell is decided by the proportion of occupied cells in its neighborhood, which is 75%. So here we introduce something called what? Randomness. Okay, because 75% to be 1. Okay, let's say this example. So now it is alive, it is occupied. So we're going to use delta to decide if the cell is going to be alive or dead at t plus 1. And now it has nothing to do with its neighborhood, because if we go back, rule number 1, if the site is currently occupied, particles dies with a set probability delta. It has nothing to do with its neighbors. Okay, let's get back. So because I gave 0.4 to delta, or 40%, right? It means that 60% with a probability of 60%, this cell is going to survive. It will still be 1. And with a specific probability, which is 40%, it is going to die, which means it will be 0 at t plus 1. Okay, so let me copy and okay. So here again, randomness. Randomness is affecting the state of the cell at t plus 1. So this is the difference between IPS and total CA. It's always 100% here. But here we have probability, we have beta, we have delta. Okay, so this is the interesting part about IPS. Okay, so this is the basic contact process. And for that value, for that death rate, if the site is currently occupied, a particle dies with a probability delta. It is interesting. There is a critical value for it. It's 0.607. There is a critical value delta C of death rate, above which the process always dies out, but below which the process will settle to an equilibrium density of occupied sites, with the density continuing to change over time. What does it mean by dies out, which means no cell is going to be alive in the end? What does it mean by equilibrium? It means that there is always living cells, and the density of living cells or occupied sites changes by time, but there is always occupied or living cells. they're not going to die or die out or extinct. So here are some results, simulation results from the textbook. Okay, we have horizontal axis here for time or ticks, 100 ticks, 200 ticks, until 500 ticks. Vertical axis is for the proportion of ones, or occupied cells, or living cells. You can say that for different delta value, we have different curves. We have different curves. If the delta value is pretty low, 0.15, it means that it's not very likely the cell, the living cells, they're going to die in future, but it's still possible, right? Because zero is 15%. So that's the reason why that you can say the proportion of occupied cells is very stable and is always above 0.8, right? We can see small waves there across time, but it's very stable, very stable. If you increase delta value, it's natural that some cells they're going to die with higher probability, right? From 0.15 to 0.3 to 45%, 50%, and you can see that the proportion of occupied cells is not that stable anymore. There is not because the death rate is increasing. It makes sense, right? Until 0.6, you can see that, I mean, the system is still struggling. But I mean, even though it's struggling, the proportion of occupied cells is below 0.2, right? It's this curve. But the system survives. There is always living cells, occupied cells. It's okay. Compared to 0.15, it's very low, it's not stable, but the system is still going. But if you change delta value to some value above delta, say, above 0.607, you can say that the system will die very quick because the proportion of occupied cells is 0, right? If you gave a value of 0.65 to the system, I mean, at least, I mean, the system can still survive 100 ticks. And after 150, it's pretty sure that the system will die. It's a flat, it's a straight line here, which means there is no occupied cells anymore. If you continue to increase it, although there is no specific values here, we have other two very short curves here, right? It means if you continue to increase delta value, the system will die out even quicker, right? Less than 100 ticks, okay? So this is basic contact process. We have two states. And they do not invade each other. Or you can say we only have one type of particle here. It's just one single particle here. It is going to invade vacant space. And we have very simple two rules to decide if a living cell is going to die or a dead cell is going to be alive in the next after the next tick. And we use delta and beta, these two probability, to decide the transition of each cell. So there is always randomness here. It's not like total say A. The majority is always the king. If something is majority, bang, after next tick, the central cell will be the majority state. Okay, so that's the difference. And you also need to know this critical value, okay, in basic contact process. Okay, yeah, this is this video. I'm going to introduce more types of IPS in the coming videos. Okay, thank you.